Welcome to the session on operator training simulators, immersive training simulators, and just simulation in general, all right? Process simulation. We will have a speaker, Ron Cisco, and as well, we will have a panel session as well with Joe McMullen. So the way we will organize it is I am the master of ceremony, Rick Riss from ARC. I'll make a presentation first. Ron Cisco will make a second presentation. And then we will move into a panel session. So ARC has studied operator training simulators and also immersive training simulators and produced a number of study reports for these. We've made a number of surveys. I think if you look in the app, you notice that the app says that you can get a copy of one of our recent surveys that was kind of describing a survey we took about how different end users found the benefits of operator training simulators, and that survey will be available at the desk inside the desk. I made arrangements to make sure they printed out a number of copies if you want to get a copy of that free insight. It's discussing things like the best practices for training simulators, what different people identified as the benefits for training simulators, and the top reasons why people didn't make a training simulator, right? And so you might find it interesting reading. So as I mentioned, Ron Cisco, Joe McMullen will be on the session. Ron is, I'll introduce him when he comes up. So the topics for today really are what's driving training simulators? Why would you bother to make a training simulator? We'll also talk about some of the visualizations and emerging technologies. We would like to be able to predict the future at ARC. We don't always get it exactly right, but we're looking at always trying to look at ongoing developments, and there's a lot of different technologies that are coming to play in the training simulation area, particularly on the visualization side. You will find that the cost of some of the simulations is certainly a big problem. So normally businesses like to invest money on things that give a very good return on investment, all right? So operator training simulators need to justify their existence. So how is it that an operator training simulator pays for itself? What is the return on investment, all right? And there's really two things that most people are looking at with operator training simulators. One is you have a very expensive piece of equipment if you are running a refinery or a chemical plant. That is the asset, all right? That asset takes raw materials and converts them to finished products. There's a large number of variables that need to be regulated, controlled, maintained. There's a lot of moving parts. There's a lot of things to worry about and a lot of responsibility for those people that are managing that, the same as a pilot that is flying an airplane, or the operator of a nuclear power plant. And also, some of the training simulators are not just for operators, they are also for maintenance staff and other technicians that might be involved. And so there you see an emerging multi-use for some simulators, particularly the immersive simulators. We will mention a number of safety issues as well. I have worked a lot in control systems myself on things like exothermic reactors, nuclear power plants, and safety is kind of an important concern, on those things. So we'll talk about those functions as well. Some of the emerging things that are driving new technology in training simulators are imaging, visualization, 3D technology, and some of the places they come from. Anybody that's seen video games recently can see some pretty impressive video displays. I'm not a big video game fan, but I tell you what, when I watch these guys play these video games, I know that several of my colleagues are absolutely addicted to their video games, and they have water-cooled video cards, and they could heat their house on their computer just because they're driving massive displays at incredible resolutions. All right, and these are just what ordinary people are paying in their own bedroom for a simulator. All right, and you ask, well, why isn't this technology being used in industry where there's a much better payback than being the #1 player on the internet of a particular video game? All right. There's always an issue associated with models and computing power. In fact, you will find some of the biggest complaints about operator training simulators are associated with the modeling of things. All right? There's kind of a rule for those people that were involved in models and simulation. It goes something like, all models are wrong, some are useful. All right? This applies to global warming. This applies to any model you have. And so the question is, often, how do you optimize the fidelity of your mathematical models for a training simulator? Just to give an example, you could spend a great deal of time modeling one control valve, all right? Control valves open and close at different rates. They have a certain installed characteristic, quick opening, butterfly, type of characteristics. They have stiction and hysteresis, all right? And those characteristics change from day to day, all right? They change from operating conditions. They could have flashing across control valves with cavitation and noise. Are you going to simulate all that detail in your operator training simulator? I hope not, all right? You have to back off, and I would tend to advocate trying to keep the fidelity of the process part of the simulation down to a relatively low level, all right? There's other aspects of training besides the training simulator itself that are needed. You will need to have operators that understand all of the health and safety issues, the environmental issues. You need to have them understand the chemistry in other ways that supplement OTS. OTS is not the only part of the operator training regime. So now I have a question for the audience. There's a lot of people retiring these days. There's a lot of talk about people retiring, and there's a lot of new operators coming in. So anybody would like to take a guess at how old Homer Simpson is? Is he ready for retirement? When is Homer Simpson going to retire from the nuclear power plant? All right? Any guesses? How old is he? All right, I'll give you the first hint. The Simpsons first aired in 1987. So the question is, what was that, 29 years ago, right? So that's 29 years ago. How old was Homer Simpson in 1987? Some people said he was 36. 36 and 29, he's 65 years old. He's retiring at the end of February, all right? So now the second question, and this one is going to go by a show of hands. You're as a plant manager at the nuclear power plant. You need a new operator. You're going to have to train this operator. Are you going to hire Lisa or Bart? All right, first of all, everybody that wants to hire Bart, raise their hand. None? Nobody is hiring Bart? He's trainable. All right, who would hire Lisa? It's only a few. I think there's a few people that's not going to hire either one. All right? All right? So, but these are the kinds of choices that we have, all right, when we're going forward. And so there's a lot of difficult choices. And the other issue is there's a lot of new millennials that are described as not being that interested in manufacturing. And when they do get a job, I've heard a number of end users complain that they are not staying loyal to the company. They want to come for 2 years and then transfer to a different position. So these are some of the difficult problems that are facing the industry in order to manage it. And the number of people that are retiring in this my baby boomer generation that I know, all right, is pretty astronomical in different places and in different industries. And they brought out the door with a lot of expertise and know-how. And it's very tedious to get that expertise and know-how into new employees. I recently was involved in an operator collaboration study. And I interviewed a number of people in the industry about that. One of the really interesting comments that I get back, I said, what are the fundamental prerequisites for an operator to be effective? All right? What does it take to him? What does he need to do that? Does he need some kind of preliminary training? Does he need a college degree? What does he need? And one of the commenters came back and said, you will never be successful unless you have at your facility enough technical know-how to understand the chemistry and physics of your process. If you don't have solid process engineers and solid control system engineers that already know how your process works and what the hazards are and how it works, the operator will basically develop his own theory about how the process works, right? He needs to learn from a mentor, somebody that really understands fundamentally where those hazards are. And I thought that was a very insightful comment. So you need a lot of infrastructure around that operator. One of the other things that was interesting in operator effectiveness was that of those programs that you put in front of the operator, a lot of people complained management edicts didn't work so well, right? The most successful programs that made an operator effective were those programs where people spent a lot of time in the control room, walking out in the field to see what the operator does and to see whatever tools you gave that operator, how the operator actually used them. If you have to treat your operator as your customer, right? Your operator is your customer. Your customer needs the right information at the right time, presented in the right way. And when you view it that way, if you are a control system engineer, you're going to build the control system he needs. You're going to protect him with safety shutdown systems. All right? You're going to empower him with the knowledge and know-how to operate safely, efficiently. You're going to give him a run plan for the day or the shift that is actionable and that you will understand what actions he has to take and he understands it. And you will also not want to hold a lot of blame to operators when they make a mistake, right? You need to be them as a partner in that relationship with operators. So those are some of the interesting characteristics I think that we see. And operator training simulators is kind of a very good way of engaging that partnership between management and operators. You are empowering those operators. There was some training programs where they trained a few people. That was actually in a South African facility. They trained a number of people about the process, and the people that were untrained were begging to get trained because they were very jealous of this know-how and expertise that was suddenly imparted on those people that were trained, all right? And that's a much better situation than having the operator come into the shift, put his feet up on the desk, and wait for the next alarm to happen, all right? You can't have that type of mentality. You need to develop a level of responsibility to those operators, and training simulators are a good way of doing this. So where are those reasons for implementing training simulators? A lot of times people are thinking operator training simulators, the only main reason was we need to have them understand how to operate the process, the physical equipment, all right? We need to know what temperatures they need to regulate at, all right? We need to teach operators how to start up, shut down the process, all right? But a good part of the training simulators capability is to teach the operator how to use the control system. I've walked in many facilities and talked to the operator and started asking them how they're using their user interface. And I find they didn't really know how to bring the right trends up. They didn't know what every button is. And believe me that the capabilities that the DCS suppliers and infrastructure control system suppliers provide on these control systems is very extensive. And it's oftentimes that even the control system engineers don't know how all of the features and functions do, never mind the operators, all right? And so there's a definite problem. And this is particularly relevant in industries like refining, where startups and shutdowns happen infrequently. A refinery starts up maybe every 3 or 5 years, assuming there's no unscheduled startups, all right? There's only usually a night and day shift and then some kind of an off shift. That means every 3 years, one of those 3 shifts gets to experience a startup, all right? All right, so people that weren't there, it could be 9 years, maybe they never experienced any startups. So they didn't have any actual plant experience. Now that's much different in a pharmaceutical batch process where they are starting up, building a batch every time. These people become very familiar with the startup procedure because they practice it. There's no choice then to use some kind of training simulator so they can practice startups. There are a lot of different kinds of display devices, all right, that the operator might have. He might have cause and effect diagram, he might show the number of conditions necessary to start a pump. All of these must be true before the start button will actually start it, all right? He doesn't use that display except at startup. He never even knew where to find it. He has to navigate around the control system. Where is that display? I know we have to start it up someplace. Training simulator gives him the confidence and the patterns, all right? He learns that patterns and speed and able to navigate around the control system. He's able to press any button, especially in a virtual environment where there's nothing to harm, to experiment and try things that he wouldn't dare try in the running environment. And the final thing here is a tremendous benefit actually for operator training simulators is that control engineers and trainers can directly see how the operator is using his HMI and using his control system. If you've ever been to a new control system factory acceptance test and you say, well, how am I going to make sure that this software and shutdowns and alarm settings are all correct, all right? And you kind of go through some checklist and everything is passing and you say, all right, it's ready to install, and we start up the plant, all right? But when you test with a control system in simulation mode, and you actually walk through every normal operation, a startup sequence, a grade change, a shutdown, all abnormal situations, also failure modes, you find that you find a lot of mistakes in the control system. You find errors in the displays, and some of them are kind of preference issues. You find that, and also especially when you involve the operators with the construction of those displays and give those operators the capability of criticizing and modifying the displays, because they will often come up with some very good suggestions on navigation, presentation order, sometimes coloration, blinking, all of the other characteristics in graphic displays that we are in use today. Another reason for implementing training simulators is safety, all right? If you take a look at some of the most significant accidents that have happened in industrial facilities, you will find that there is some pretty substantial costs and penalties, legal fees, deaths, all right? Chernobyl, 4,000 people were estimated to have died, $200 billion worth of damage. Fukushima, nobody died initially, but 180 future cancer deaths are predicted. $120 billion of damages, all right? It's a Bhopal accident, 8,000 people dead, all right? Texas City accident, 17 dead, some different estimates here, but some maybe $7 billion in lawsuits. Now, a lot of people are complaining, managers are complaining, operator training simulators are expensive. But if you look at the cost of these accidents and you look at the likelihood that operator training simulators might have helped them avoid them, and there are some that are particularly beneficial, like the Texas City accident, all right? Training simulators were specifically identified as lack of training was a big problem, an instigating factor. But if you look at the cost of all the damage, you could build an operator training system for every single facility in the world, all right? Even at $1 million a piece, all right? These are thousands and thousands of millions of dollars of damage, all right? So this is one of the arguments the probability is that it's a low frequency operation. It's not going to happen in my facility, all right? It only happens in somebody else's. But if you look at statistics, you can look at Wikipedia, the most significant accidents. You don't see that accidents are really declining because of new technology. There are still a lot of accidents occurring, all right? So in any event, safety is certainly an issue. I had worked on some nuclear power plants in China and was very interested in the Fukushima accident. I was actually flying in an airplane at the moment of the tsunami, landing in Beijing, all right, and followed the whole program. And one of the guys I worked with on my project actually was in Fukushima facility at the moment of the tsunami, and he lived there and eventually, after 3 or 4 days, was managed to get back to Tokyo and get away from the facility because there was nothing he could do. But one of the interesting things, there was an ARIVA report, there was an IEEE report, there was a PBS video made, so there was a Union of Concerned Scientists book written on step-by-step of all the situations in Fukushima. The problem with operator training in Fukushima, now first I should mention that all nuclear power plants operators are required to go to operator training simulation. There's no such requirement, and I don't even see a lot of momentum for that in oil, gas, and chemicals, all right? There's not any legal requirement. Pilots are required to train on simulators. You don't want them to fly the plane and say, is this the right lever? Is this the throttle? Is this you got a lot of investment to protect, right? And so from my view at ARC, from what I've looked at these studies, I could have to argue that we're probably not spending enough money on OTS systems, although we also see a lot of money being spent in that direction these days. So, for some of the reasons we mentioned. But there were a number of particular problems at Fukushima. The first is that the control room went immediately black, all right? The reactor shut down, no problem. It was shut down, the rods were dropped, uranium stopped fission. But as in all nuclear plants, the remaining radioactive byproducts in the tubes continued to generate 6% of full rated power heat. You must cool that reactor, even in the shutdown condition. You must cool it, all right? And without electric power to run pumps, there was maybe some that could generate steam, a steam driving a steam turbine, the driving of pumps, that lasted for some time. But they didn't know a lot of things. They had no instruments, they didn't know levels. These were not things you would call in normal SOPs, all right? So they were going out to the parking lot and getting batteries out of cars and jumping them together just so they could read instruments, all right? These are situations that you didn't plan for. One of the interesting things here, as the NRC looked at lessons learned from Fukushima, is that they really want to emphasize training in the abnormal situations to a much larger extent, all right? And this is hard to do because you can't anticipate every abnormal situation. But one of the things most people don't realize is there were 2 nuclear power plant locations near Fukushima. There was the Chai plant, and that's the one that made the news and had meltdowns at reactors 1, 2, 3, and they are very concerned about the spent fuel pool. 10 kilometers south of that is Danai. Those operators figured out how to get electric power and cooling back to the reactors. Those reactors were saved. So there were 2 different operators fighting substantially the same problem. Both had undeterminable stress of abnormal situations. These guys were up for 48 hours, and events would come up. You can't go to sleep. We have to decide now, what are we going to do next? If you don't do this, it's immediately going to be a big problem. You can't go to sleep. Find an answer to this problem, all right? And so they struggled valiantly, but and some could argue that had they taken actions faster, the damage might have saved some or all of those reactors, if they only could have anticipated and played back and gone back and changed their course of actions, which, by the way, you can do in some of the simulators. If you've made a mistake partway through, we can play back. We can go back to that point. You can try again, all right? But there's no trying again at Fukushima. So what's some of the new things driving the technology? You can buy a product called Google Cardboard, $10. All right? You can put it in front of your iPhone or Android, and they can put 2 screens there. You can have 2 different lenses. For $10, you can make a 3D demonstration. It's not highly effective, although it is very impressive. I'd never used one of these, but they tell me that the reason they didn't put headbands on it is that you're going to get dizzy if you follow here, because it uses the accelerometers in your phone, not something more sophisticated. But if you get an Oculus Rift, and I've actually put an Oculus Rift on before, and I've walked through buildings, and I walked underwater actually, and bumped into trees and had to walk around them, and with a little Xbox controller. And when you look this way, the screen changes which way you're looking, and it's pretty fast. I could imagine the resolution could get eventually to the point where you hardly know that you're not in a real situation, all right? And so these technologies are coming fast, all right? There's I know a number of people even in the room here, right, that are using these gaming engines, all right? And you have a gaming engine works with multiple different headset types, all right? So as long as you use a gaming engine as the center of your simulator, it is compatible with a number of different 3D models, compatible with a number of different headsets, and you'll see a lot of technology going in this direction, all right? Some of those have been done in cave simulations. There are cave simulations that vibrate the floor. There's one cave simulation I think ExxonMobil did in Qatar. They actually inject H2S into the room so you can smell it. All right. There's a new technology that I saw recently here where you can project almost what's a holographic image, so you could have a telephone conversation as if you were a real person to person. This is room to room technology. You know, you can obviously then, in a lot of simulations, choose an avatar, however you might want to be. You can be tall and strong. You can change whatever person you want to look like, and you can operate in 3D. All right, a 3D space like video games. It's a multiplayer game. One of the other technologies is, well, how do you get all these beautiful 3D models that we've seen? All right. And there's interesting that companies in the mining industry, particularly Caterpillar Tractor, has some very impressive simulation and training systems, you know, that are much further advanced actually than we see in a lot of the process industries. But you can drive a truck like this around the plant. It has a GPS locator. It has a LiDAR camera to take 3D image. It can create a 3-dimensional point cloud. You can also use camera pictures. In fact, there are technologies to simply take camera pictures, possibly with a drone. No LiDAR involved, and build 3D models, all right, of the plant. Still a little bit expensive, still a little bit time-consuming, you know, to build some of these things. But in principle, you don't have to have the 3D CAD models of the buildings and structures necessarily. Obviously, that's an easy way to go. If you have those 3D CAD models, yes, by all means use them. So you see a lot of E&C firms that have the 3D CAD models that they needed to build the facility, and that's why you see these immersive simulators used probably more often in the greenfield projects of a brand new project. Particularly those things are very hazardous, like oil rigs, etc. So another emerging situation is to have simultaneously a field operator and a console operator operating interactively, all right? So a field operator can see physical equipment, you know, the simulation is simulating temperature, pressure, and flow, all right? So when he goes by a pressure gauge out there, so pressure gauge is representing the actual simulated pressure in the pipe or vessel, all right? They can be in 2 separate rooms with walkie-talkies to emulate as if they were doing it. I learned just yesterday from one of the guys that, how come I'm trying, when I like to do this at ARC, well, I want to run that. Give me the controls. I want to see how you're working, all right? And I learned that, well, how come I can't go faster? I'm walking so slow. Well, if you went faster than the actual time it took to get from the cooling tower to the shutdown switch because you got a fire, then it's not realistic. So we had to adjust things like walking speeds and things to be accurate simulation. And so you could put quite a number of scenarios you could involve, you know, scenarios for maintenance engineers, you know. A maintenance engineer shows up to a transmitter to calibrate it. Sometimes he needs 5 different pieces of information. He needs the spec sheet, the calibration sheet. He needs the model and part numbers. He needs to know the issue of whether he has spare parts in maintenance and stores, etc. All of these kinds of things will start to get into some of these. It gets a little bit beyond training simulators even, I suppose. Now, I just kind of want to take a look at just how far our technology has come. It's hard to imagine that hard to imagine you could get someone to actually play Pong today, all right? I mean, how boring can you get? You know, I got to hit this thing, you know, it's just not quite so exciting, you know? But video games have definitely enhanced the ability, and there's a lot of displays. Even the hardware for gaming computers, you know, NVIDIA and all of these hardware developers are building for games. These are the same technologies that are used. So I wanted to point out this little gadget on the left is called the DSKY, D-S-K-Y. That is a display and keyboard. That is the human interface. By the way, in my opera collaboration study, the #1 most important tool for the operators to be effective is the HMI with alarming and displays. Obviously, control strategies are very important. But imagine that you're going to land on the moon for the first time. No one ever did it before, and that's the user interface that you have to land on the moon. You're in an Apollo lander. You don't even know which way is up, all right? All right? This is the first time you ever did it, all right? This is the first time anyone ever wrote software to that point. All of this hardware behind here is new. So program is stored on rope memory with magnets that were weaved by women, all right? Zeros and ones, they wove the memory so that they could have, so the program itself couldn't be corrupted because they had no way of storing the program reliably, all right? In this display, you see the 06 number is the verb. The 60 number is the noun. And there's a list of verbs and nouns. And this one was to set the value. Item 60 was the noun of the vertical velocity, and that was displayed in the zeros system. In off mode, it was doing nothing. All right, so there is a verb and a noun and a keyboard and an enter. Everything was operated from this to do. Now, do you think that guy needs some training to run that? You know? You think they ran a lot of simulations and testing? For sure they did. So here's a common display. You know, we still make most of our displays based on P&ID drawings, right? So these operators also need these displays. There's a lot of things that are often hidden here, overlays, certain features and functions. How are bad out of service or disconnected points shown here with background coloration and blinking, et cetera? And how do you navigate, you know, and all of the standards there. You know, there's an ISA 101 standard of how to build graphic displays. This can help. I'm not sure that that standard is going to apply to the displays of the future. The future operator, I'm thinking, is going to have, you know, 3D glasses, and he's going to be walking in and out, and he's going to be able to see where the field operator's hands are, all right? All right, on his display, all right? I'm not quite sure which way the future is going, but it's going to be different, all right? So what are those differences? You know, there's a lot of development in 3D and virtual gaming. You know, obviously there's just the online modeling is an issue. And, you know, with regards to online modeling, as I mentioned, you have to optimize fidelity. You know, some of the biggest complaints about why we didn't build the simulators, it's too expensive to maintain it. And one of the other things is that, you know, control strategies change. Oh, I adjusted the alarm setting. Oh, I adjusted the tuning parameters. Oh, I adjusted this extra override to protect it. And they change constantly. You have to go to the real control system and take that software and bring it out here. Now, almost all the DCS vendors can run that real software, the exact same displays, the exact same controls and alarms, and run that in a virtual machine and connect that to a training simulator of some type, all right? And that's really important, all right? So updating is hard. Linking the field and console operator, I think I mentioned as well, all right? So to finish off here, these are the strategies for success. You must have a technically solid engineering understanding of your process. You must have somebody that has to train the trainers, all right? You must have something that you can count on as being accurate and fact about how your process works, all right? The simulation modeling tools need to be easy to maintain. Don't go overboard with simulation. You can simulate the death, all right? And you could spend untold amounts of money to get more and more fidelity. And when a lot of times the training simulator is part of the training simulator is to train on the control system. You didn't need a high fidelity to train on the control system. You need to navigate and press and see how the controls work. And you need to test on off mode situations, you know, off normal. Virtual systems and 3D model, you know, with exact control systems, exact control configuration. It's much less desirable to port the control strategy over to the simulation. This PID is not going to be the same as that PID. It's really much less desirable to do that. Use OTS for control system development and testing, because if you don't, that means you're doing development and testing on the running process. This is not a good idea, but it is done everywhere, or often, all right? You want to test and evaluate how your control strategy is going to work in a safe environment instead of testing it. Oh, I accidentally closed the wrong valve, you know, and it's easy to do, all right? Train all types of workers, not just operators, and develop a comprehensive training program possibly using gaming technology, you could imagine how sophisticated training programs might get. So, any case, myself and Janice Abel are both covering the operator training simulation space. We are available for questions. You can find us on the ARC app. I'm going to turn the presentation over to Ron, and appreciate your time. Hope I gave you some ideas.